Hi, everybody. So in this video, we're going to talk about gas exchange. Now, to understand gas exchange, we need to remember that we are relying on diffusion to move these molecules across the membranes. So because we are relying on diffusion, we need to make sure that we have different pressures, or in order for diffusion to happen, we have to have different amounts of the gas on either side of the membrane, which means in gaseous terms, this means we're going to be relying on how much pressure of gas do we have in this particular place versus how much pressure do we have in this particular place. If we are higher here and we are lower here, well, then that means we're going to move from high to low. So if we need to get oxygen into the blood around the alveoli, that means the oxygen concentration in the gas that we are breathing in needs to be higher than the amount of oxygen that is actually left in the blood, or than is in the blood. So if it is higher in the air that we breathe in, it will travel into the blood. Now, this picture here is showing you some of the partial pressures of the gases kind of around you right now. Now, here in Kilgore, we are basically right around sea level, within 30 or 40 feet of sea level, actually, so it's pretty close. Okay, so we're right around sea level, so we're going to be seeing a partial or an overall gas pressure of 700 millimeters mercury. Okay, so remember that pressures are usually listed in this kind of millimeters mercury. Now, around 78% of the air that you are breathing in right now is nitrogen. Now, nitrogen, we don't really use gaseous nitrogen for anything. In fact, very, very few things can actually use gaseous nitrogen to do anything. Okay, and that makes up almost 80% of the air that you are breathing in. 21% of the air that you're breathing in, or 20.9%, is oxygen. Only 0.04% is CO2. Okay, so 0.04% is CO2. And then an average humidity kind of everywhere is this 0.46%. Now, here in East Texas, it may be a little higher at times, maybe a little lower at other times. So after a big rain and a bunch of that rain is kind of getting burned off and going up into the air, and that raises that humidity, well, then this number here would change. Okay, so this is kind of what we're looking at when we look at humidity numbers. Okay, but ordinarily it's around 0.5%. So if we need to get oxygen into our tissues, that means we have to have a pressure of oxygen in our blood that is going to be lower than 159. If that's the case, that means the oxygen will travel from the air that we're breathing in to the actual blood. And we're relying on this to happen in the alveoli of our lungs. Now, we get to that 159 by basically taking that overall pressure and multiplying it by the percentage of the air that is actually composed of oxygen, because the overall air pressure isn't what's going to push the oxygen in. In fact, it's only going to be the actual pressure of the oxygen itself. So we look at each one of these independently. So say we look at that atmospheric oxygen of that 104. Well, if we look at the pressure of oxygen in our blood, remember the oxygen most of the time in our blood is going to be bound to hemoglobin. It's ordinarily going to be around 40 of this deoxygenated blood that is traveling into the lungs. So 104 is obviously higher than 40. So it's very easy then for the oxygen to travel from the air at 104 to the hemoglobin at 40, and then try and make these two numbers get closer together. So the oxygen will travel across and then bind to the hemoglobins. So oxygen travels then into the blood because we have a difference in pressure, higher pressure of oxygen in the air that we're breathing in versus lower pressure of oxygen in the, or bound to the hemoglobins in the blood. Much different. So 104 higher than 40. So we're going to see oxygen move in that direction. But we'll also see the same kind of thing happen with other things. So let's look at pressure of CO2. Well, pressure of CO2 in the air that, or in the blood that is coming back around, is going to be around 45 in our systemic cells. So pressure of CO2 in our systemic cells, pressure of oxygenated blood is going to be around 40. So that means CO2 will go from 45 to 40. So it will move into the blood. So we're going to carry this now CO2 rich blood up into the lungs where, well, 45 is actually quite a bit higher than 0.04%. So the CO2 will then leave. So it's really going to be kind of the movements of these molecules is going to be based off of these partial pressures. So pressures of oxygen in the alveoli is now 104 because that's the air that we're breathing in, remember. Pressure of oxygen entering the capillaries of the blood, so entering the blood, is 40, 104 higher than 40, so the oxygen will move down. Now, we typically say that the pressure of oxygen in the alveoli is going to be constant. Mostly this is just because we are continuously moving air. We're constantly breathing in, okay? Or we breathe in a lot. So this air is constantly being refreshed. So it's typically going to stay around this 104. There may be a little bit of variances here and there, but we're breathing in so much that it's going to stay relatively constant, or at least that's the whole idea, okay? CO2 in the alveoli is 40, and the CO2 rich blood is 45. So we're going to see the carbon dioxide diffuse across. And we try and do this until the blood level equals the alveoli level. So we're going to continually move that CO2 out of the blood and into the alveoli so that we can then breathe that air back out. So what we are relying on then for gas exchange is to have a difference in pressure in one place than the other. We are relying on diffusion. In order for diffusion to occur, we have to have a higher concentration in one place than we do in another. It will move from areas of high pressure to areas of low pressure, okay? So oxygen in the alveoli of our lungs here, 104, oxygen poor blood at 40, so it moves across, okay? Now, we also need to keep in mind that the same thing is going to be happening kind of at the tissue level. So this now oxygen-rich blood will go down to the tissues. Let's see if I can find that slide again. Where'd it go? So the oxygen-rich blood now at close to 104 is going to travel down here to our systemic cells, where their partial pressure of oxygen is now 40. Well, so which direction is it going to go? It's going to move from that 100 towards the 40. So this is what we're expecting to see kind of every time, okay? Now, in order for this process to be very, very efficient, we need as much surface area as possible. We need as much surface area of the oxygen-rich airs meeting the oxygen-poor blood. We need as much surface area for oxygen-rich blood to meet oxygen-poor tissues, okay? So we do all of this in our capillaries because capillaries are going to give us much larger surface areas in the tissues and in the alveoli. In particular, though, we have lots and lots and lots and lots and lots of capillaries around the alveoli of the lungs. Those alveoli being really, really thin give us lots of surface area because we just put whole bunches of these little clusters, all of which have a lot of surface area, so that we can get as much of this stuff to happen as possible, as quickly as possible. So we get around 70 square meters. So this is 75 square yards of surface area here, just bundled up into the lungs of your chest. That's how much space we have. Now, we don't use all of it all the time. Instead, we can dilate or constrict the bronchioles based off of levels of carbon dioxide or based off of levels of, well, actually, yeah, we really mostly just use carbon dioxide because we have good measurements for the amount of carbon dioxide we have in the blood. So say you want to go out and do some exercise. Well, if you do some exercise, you're going to be burning more oxygen, which means the blood that's now returning to your heart is actually going to be more oxygen poor. When that more oxygen poor blood comes into the heart, it basically sends a signal or comes into the lungs rather. It's basically sending a signal that says, hey, we have really high concentrations of CO2, which means we also likely have low concentrations of oxygen. So that means the bronchioles can dilate so that we can get more of that CO2 out, and also we'll open up more bronchioles so that we can allow more air in. This is one of the reasons that when you're exercising, you don't just breathe faster. Instead, you do breathe a little bit more quickly, but instead you make up for that oxygen need by breathing more deeply. And one of the ways that we can breathe more deeply is by opening these bronchioles to allow more of the alveoli surfaces to be used. So if you have any questions about gas exchange or respiration or anything else in the course at all, please just let me know. All right, see you next video. Thanks. Bye.